Alright, so here we have an ester, a similar name to an ether, and it is kind of similar. Now the only difference is that it has a ketone connected to it now. When this happens, we call that an ester. Now, of course, when it comes to naming an ester, which you will need to know, you have to know which side is the parent side and which one is the substituent side. Now, why this might be a little complicated is that unlike an ether, you actually can't say, oh, this is a parent side, because this is a parent side, because this is the side with the CO. So as long as a side has this, it's a parent side, and this is substituent side. So for example, this will be a proper ethanoate. Yeah, ethanoate. So yeah, you will need to add an O8 at the end of an ester. And I believe that's it when it comes to naming them. Esters are interesting because usually when combining a carboxylic acid and an alcohol, you would get an ester. Just keep that in mind. I will go over that. I can erase it. Greetings, ladies and gentlemen. My name is Christopher Michael, and today I'm going to be teaching you about organic chemistry. So let's begin with what is organic chemistry. Well, organic chemistry is the study of monomers that contain carbon atoms, with this being a main example, which also known as ethane. You might have heard of ethane before. That's probably the one. And I'm going to make it my job to teach you how to name them, how to add them, and how to add them. Alright? Alright. So let's begin. By the way, quick warning, there's going to be a lot of cuts in this video because I stutter a lot and I forget things very easily. So between every section, there's going to be a cut. So if you don't like that, sorry. So let us begin with something simple, numerical order. As you can see, we have methyl, ether, propyl, butyl, pentyl, hexyl, heptyl, and octyl. Now, of course, there's plenty more, but by the time you get to a monomer containing more than 8, it's not going to be a monomer. It's going to be considered a polymer, and you'll probably have a bunch of different names, but just know that numerical orders for everything above octal do exist. So let's begin. Octal, methyl, propyl, butyl, pentyl, heptyl, heptyl, and octyl, of course, are based on the carbon chain. Now you may be wondering, what is a carbon chain? Well, a carbon chain is the longest chain of carbons in a monomer. For example, we have 3, so it's a propyl. Now, it isn't as simple as, oh, the line. No, don't get confused. Yeah, let me give you an example. Alright, so what we have here is a monomer, and of course it's a monomer. Ignore me. So what will we name this? Now, some people might say, oh, 1, 2, 4. That's clearly a butyl. However, that's not the case. It's actually 1, 2, 3, 4, 5. A pentyl. The reason why is because when it comes to chains, it doesn't matter what direction it goes in. It's like an axial chain. Sure, you can hold it straight, but you can bend it there, and it will still be considered a chain. And because this is the longest, we will accept that. Now you will be wondering about the. Yeah, I'll get to that in a moment. So yeah, this would be a 3 dimethyl pentane. We'll get to the aim part in a bit, but let's focus on this part here. As you can see, since these two metals are connected to this middle one, we call it 833 because it's the third one. Now let's say if instead this was what we had, then we will call it a 2 diameter. Now you may be wondering, but couldn't you also say that it's a 3 diameter? Oh, that's supposed to be butane. But couldn't we say that it's also a 3 um diameter butane? Well, the answer is no, because we will always look for the lowest chain, which just so happen for the lowest number that we can put in a name. For example, since this C can be considered a 2, then we will use 2 since 2 is lower than 3. That's important to remember, alright? And of course, when it comes to memorizing these names, when it comes to these ones, these are easy. Penter is a pentagon, hexter, hexagon, hepter, heptagon, octer, octagon. They are the basic ones, the things that you expect. The main problem will come with these four: meter, ether, proper, buter, because things have to be complicated in life just because. So yeah, don't worry about these ones, worry about memorizing this. And you may say, but Michael, how do we memorize them? I don't know. Look, I have a weird memory. Sometimes I remember things, sometimes I don't. And so, in my experience, if you want to memorize them, just focus on trying to remember this. You don't have to memorize them immediately. Take your time, and eventually, they'll come to you extremely easily. Like at first, I would always have to check what was what, but now I can just easily write, oh, that's a butane. All right. Alright, so now let's go over alkanes. So as you can see, here we have a propane. As what makes this a propane, not an propene or propine, is that it only has single bonds between the carbons. Of course, let's say if there was a double bond, then another atom double bonded to a carbon, you wouldn't count them because it's only between a carbon and carbon. So, as you can see, this is as basic as an alkane can get. So let's quickly go over how you write something like this while we have something as simple as that. There's two ways to write it, the simplified and the extended. The simplified will be written as CnH2n plus 2. Alright, so the N here represents the amount of carbons. Here we have 3 carbons, so we have AC3. Now with the H, 2n plus H, so that will be 2 plus 3 plus 2. The reason why is because for each carbon has at least 2 carbon. Each carbon has at least 2 hydrogens. My apologies. Or at least normally. However, as you can see, the N carbons have 3 hydrogens. So we account for that by adding this plus 2. Adding this one and this one. So, for example, 2 times 3 is 6 plus 2 equals 8. Simple. But that's the simplified version. If you're asking for an extended one, you write CH3, CH2, CH3. As you can see, you separate them by the atoms connected to the carbon. Now, let's say if you had something like a butane or higher, you could write it as CH3, CH2, to CH3. The reason why we can do it for that is because the CH2s are right next to each other, so we can simplify them by putting them together under parentheses and then a 2 next to it. Alright? Alright, let's move on to an alkene. An alkene has a double bond between the carbons, which makes it an alkene. Now, something interesting about alkenes and probably alkynes, I don't remember if it applies to alkynes or not, is that it can have the prefix trans or cis. Now, let's take this one for example. As you can see, this carbon is facing downward and this carbon is facing upward. So that's a trans butane. The reason why it's a trans butane is because, well, they're in different directions. Now you may say, well, what if you had something similar for an arcane? Well, then it wouldn't really matter because since it's single bond, it's incredibly flexible and can easily torn and stuff like that, but a double bond cannot do that. So it's stuck like that, so that's a trans. But it's not just a trans butane, it's a trans butene. Now you're wondering, what's a 2 for? Well, it's signifying where the double bond is. It's connected to the second carbon. So yeah, you have to remember to put that between the but and the in. If I'm accidentally call this an arcane, I'm sorry. Now you may say, well, what does the arrows have to be? Well, I'll show you an example of it with an alkyne. So an alkyne is, of course, as you could probably guess, an example of a triple bond within carbons. And as you can see in this example, this triple bond happens immediately after the first one. But if you really think about it, it could only take place between the first and second one, no matter what order. So this would just be, sorry, so this would just be a propine. No numbers, because you already know where it's going to be. It's always going to be there. So that when it comes to these two, if it's a ethene, ethyne, propene, propine, you will never use this number here because you already know where it's going to be. Alright, when it comes to the simplified form, when writing these ones out, there will be CnH2n, because we no longer have to worry about the extra 2, since due to the double bonds, these carbons can have one less hydrogen. And when it comes to the triple bond, since now they have even less hydrogens, this becomes CnH2n minus 2. This is pretty important because, it makes life much easier. And when it comes to writing them down in the extended form, there are two ways to do it. For example, CH3, CH, CH, CH3. You can leave it like that, or you can do CH3, CH. It really depends on your personal choice. Like, either of this is correct. Yes, probably this one is going to be much more clear on what it means exactly. Alright? That's it. Alright, so let's quickly talk about cycloalkanes. A cycloalkane is basically an alkane that connects to its other. For example, this is a cycloalkane, or a cyclobutane, because it has four, and of course it's in a cycle. Now, of course, the prefix cyclo can never go for a methane or a ethane, because you can never have one in a cycle. Now, of course, something interesting about the cycloalkanes is that they actually have this property similar to um alkenes, in which they not only they say a lot with alkenes, surprisingly enough. For example, CnH 2n. Yeah, it's written the same. It's the same type of formula that you'll get when trying ACE and alkene, and you would definitely write it like that. Not usually. Cycloalkenes are a pain to draw. If they want you to do an extended version, just put in parentheses so they know. Alright, it's in a circle, are bonds together. But another interesting thing that it serves with alkenes is that it has the trans insisting too. For example, let's add chlorine to this. So we have this chlorine, which is at the bottom of this carbon, and this chlorine, which is above this carbon, making it a trans 1,2 dichlorocyclobutane. As you can see, the cyclo will go before the butane part, where the trans goes before the entirety. And as you can see, there's a 1,2 because 1,2 doesn't matter in what order as long as there's a 1 and a 2, and the di because there's two chloros and chlorines and chloro. That's how you write something like that. In case you're wondering, there's also iodo, fluoro. Yeah, fluo. Is it fluoro? Okay, I ruined this whole take fluorine. If I did not ruin this take, go look it up yourself, alright? I'm too lazy to think about it. So let's move on to benzenes and phenols. Now, of course, if you are a nerd like me, you will recognize the name benzene because, of course, it was the red substance in Subnautica. Probably. Oh, terrible memory. But yeah, this is what a benzene looks like. Almost. It's just missing something. A nice ring. Now, what this ring means is that it has a bond order of 1.5. What that means is it basically usually looks like this, which, or at least that's how some people write it, but the circle one is better. And the reason why is because it doesn't really have double bonds. Instead, it has mainly single bonds, but electrons floating throughout it, kind of working like a double bond in some places, but they're so delocalized, they don't stay in one place, they move around, which leads it to having actually CnH2n, actually just CH2HN, because as you can see, each carbon only has one hydrogen. And benzene will always be a C6H6, because you can't exactly have it more. Like maybe you might be able to make a what's it called? An octane into benzene? Actually no, because this really is just called a benzene. So it's very unlike, so I'm pretty sure it's only with 6. Prove me wrong or something. Alright, let's quickly talk about the prefixes ortho, meta, and para. You will likely not see them, or because they aren't that important, but just in case you do, here's a quick rundown. So let's say we have a chlorine here, 1, and another chlorine here, 2, and a cyclohexane. This will be an ortho 1,2 dichlorocyclohexane. Because ortho is basically 1,2. If that applies to a cyclohexane, no matter what, it's going to be an ortho. But what if it doesn't have this, instead has one here on the third one, where that will be a meta 1,3-dichlorocyclohexane. Or let's say it doesn't have this one either, and instead has one on the fourth one, where that will be a para 1,4-dichlorocyclohexane. So yeah, don't worry about this. You will likely not see them, but they're good to know just in case you hear them and you're curious about it. So yeah, I won't worry about memorizing them. Honestly, the only one I knew by memory is meta, but the only reason why is because I like meta references in media, and also I grew up in Meta, which is a departamento or state in Colombia. Alright, now we can finally get into the functional groups and classes. They're basically things that might apply to a monomer depending on what's found on the carbons. So let's start with alcohols or hydroxyls. Now, a way I would say to remember what a hydroxyl is know what an alcohol is. An alcohol contains OH. OH being a part of water, hydroxyl. Alright? Just try to remember that hydroxyl contains an OH. Alright? And as you can see, here is an example of an alcohol. Now, how your name is an nor. As you can see, we replace the E and add an or to it. Now, of course, the comes to ethanol, it's of course always going to be called ethanol. But let's say after that is a nor C, and there's a more, and this is no longer an ethane, a propane, where this will be now known, propane, my God, a propan tour, because it's on the second one. Yeah, just make sure to make the distinction. Because if it's on a methane or ethane, don't worry about it. Anything higher, make sure to write that. And if it's in more than one place, just separate the two numbers with commas. I don't believe you need to write die or three or stuff like that for it. So now just worry on that. Alright? Oh, quick, before I forget, let's talk about tertiary, primary, secondary, and tertiary alcohols. So, here we have an example of a primary. As you can see, this alcohol is connected to a single C, which will be represented by CH2OH. So yeah, if it has this, it's a primary because this carbon, it has a lot of hydrogens, blah blah, and it's very reactive, by the way. So probably made that specific. All right, now this is a secondary alcohol because now it has one hydrogen, aka CHOH. So yeah, so you can see since it has one less hydrogen, then it has one. So it's a secondary now because it's now much less reactive. And of course, let's say this would be what's it called? A tertiary alcohol, which from what I know don't tend to react much. Now, of course, that will come very handy when you're talking about oxidations, and we'll get to that eventually, don't you worry. And so yeah, when it comes to alcohols, just know that if you want to write it as I thought, the OH will come after the H's, alright? And it, for example, let's say if it's in the middle, CH. So yeah, just write it like that. Like that, they'll know that this OH is connected to this. And since this H is not with the other H's, they'll know, oh, it's connected to the oxygen, not the carbon. So yeah, make sure that when writing or alcohols, the OH is written as an OH, not an HO, unless under specific circumstances. Oh, and very quickly, if you're going to draw it, don't draw one like this, right? The line should always be facing the oxygen, never the hydrogen, and never the space in between, since the carbon is connected to the oxygen, not the OH bond or the H, alright? Alright. Alright. Here we have an aldehyde or a former. Now, of course, when it comes to the former, that's going to be much harder to remember. The main reason why I remember that is due to this yoke I once heard on the internet. The opposite of formaldehyde is casual dejacar. That just makes me laugh. I don't know. I mean, yeah. So if you're, unless you're a dork like me, you're not going to remember that. Just know, you know what? Just try to remember former as it is. If the castle the Yekor will help, go for it, but I have faith it won't. But as you can see, an aldehyde is formed by this part right here. A C double bonded to an O and an H. This will always be what makes an aldehyde. And such, the CHO will double, the CHO will always be at the end of a chain, or as Isaac said, the start of a chain, because this carbon will always be number one. So let's say you have here a chlorine. This is going to be a 3 chloro propanol by way arm. So it's similar to alcohol but with an A instead of an O. And at the end, yeah. So yeah, 3 propanol, because this will always be number one. And such in such you will never need to write the number there, because it's always going to be the same. Alright? So yeah. Just know that this kinda breaks the rule. Just kinda. And now, of course, an interesting fact about aldehyde. If you oxidize a primary alcohol, you get an aldehyde. That's neat. I'll go over more about it in a bit. Alright, so now we have a ketone or carbonyl. Now that name is a little strange and it can be hard to remember. Just know that, of course, it's a carbon, the and an O. So the carbon is connected to an O, specifically an oxygen and nothing more. You see why that becomes important later. Now, of course, this right here is a ketone. As you can see, it's a carbon chain, but one of the middle carbons is double bonded to an oxygen. Now, of course, this will be a propanone. And because that, give me a second. And of course, because that O can be in any of the middle ones, that means that you will actually do have to remember the ones and twos. For example, this would be a 1, 2, so that's a pen, tunon. Yeah, just remember, same thing as always. And when it comes to a ketone on a propane or butane, you don't have to worry about it. It's always going to be a 2 for those. Only after pentanes will you actually have to remember to write a 2 or 3 or whatever. Alright? Is there anything else for ketones for the moment? No. Yes. Just know that this carbon won't have any hydrogens connected to it. That's about it for that. Alright, now we have a carboxylic acid or a carboxyl. This is what I was talking about earlier. You will know that a carboxyl is of course a combination of carbon and oxyl. Oxyl of course referring to a hydroxyl, which is an OH, and a carbon like carbonyl, which connects to the C double bonded O. As you can see, it's similar to an aldehyde in the way that instead of an H here, it's an OH. And just like an aldehyde, that one's always going to be number one. Now, of course, how you write that would be, for example, this would be an ethanoic acid. Yeah, fun, fancy name. Yeah, so just add oic acid to the end of it. And you have it. And of course, to write it, you write it as COOH. Neat. Alright, ethers. When it comes to this, the name does not matter. You do not have to memorize the name, but you should know what an ether is. What an ether is basically when a monomer has two different parts that are separated by a single oxygen. Now, of course, when it comes to the second part, you have the substituent and the parent. The parent is the longer side, so 3, and the substituent yields shorter side, the 2. So this will be an ethoxy propane. So, yeah, an ethoxypropane. The oxy will be at the end of the substituent, replacing the il that would normally go there. Sorry about that, I just scratched my mic. So yeah, when it comes to names, you do not have to memorize it. Just just know that the an ether only has an O in between 2 carbons. Alright? That's the only thing you have to remember. You can remember this if you want. Why would you? But you can. Right. So amines and aminos are actually kind of interesting because they involve nitrogens. That's right. An NH2 or an NH3, I guess. Now, of course, just like alcohols, you have a primary, secondary, and tertiary. But instead of depending on the carbon, it now depends on the nitrogen. So if a nitrogen has 2 hydrogens or is connected to just 1 carbon, it's a primary. If it's connected to 2 carbons and has just 1 hydrogen, it's a secondary. If it's connected to 3 carbons with no hydrogens, it's a tertiary. I recommend you remember that. Probably. That's probably important. And when it comes to the names, amine, amino, seriously, it's if you know what an amino acid is, you're going to remember what an amino is. And then just replace it with an E and you have the name amine. That's so easy. And while we're at it, let's say I actually don't know how to write an amine, oh dear. Alright, let's say we have this. Yeah, I can actually write them. This will be a ethanamide. Amine. Ethanamine. My apologies. Amides we'll see in a second. Oh yeah, that's how you write them normally. I have no idea how to write those. I'm so sorry. You will have to look that up for yourself. I mean, in my class, we already moved on from organic chemistry, and there were ones that we have to name that. So I wouldn't worry about it, but you can always just double check on the internet if you want. Alright, here's an amide. Notice something? It is very similar to an ether, ester, in the way that there's a C connected door bonded to an O and connected to another thing that isn't a carbon. Indeed, it's very, indeed, now instead of just an O, we have an NH2, which makes it an amide. Writing it, it would be an ethanamide. I mean, look guys, I don't know what to say. It's literally just, if you have a CO and one of these, it's an amide if they're together, you know? Oh wow, not what it is. Alright, now we have addition. Yay, we're finally out of classes and functional groups. So, what is an addition between a monomer and a molecule? That. Let's go over it. As you can see, here we have a door bond. It has to have a door bond for it to work as an addition. If not, it's going to be a substitution reaction, we will get to in a moment. Here we have a molecule. I'm using HOH as an example here for a very specific reason. So we are going to need a catalyst, of course, to make this happen. Now the two big ones are nickel and platinum. Now when it comes to platinum, that's easy to remember. If you're a nerd, of course, there's platinum trophies, platinum relics in Crash Bandicoot, Pokemon Platinum for Pokemon. and a lot of other stuff because platinum is surprisingly seen as a step above gold in the bronze, silver, and gold tier. When it comes to nickels, just think of nickels, man. Or nickelback, that'll work. Just know nickel and platinum are the two catalysts for addition reactions. And as you can see, here we have a propane, a propanol, my bad. Now you may be wondering, could these oils go on this side? Well, the answer is no, due to a rule known as, what's his name? Markovnikov. Oh my. Markovnikov's rule states that the hydrogen in a molecule is going to go to the carbon with the more hydrogens because that will lead to a much more stable um, monomer, and leaving the other side to just join with a carbon. But you may be saying, why would only this one break and not this one? Or simple, because that's how water works. It's going to give its acidic acidic side and basic side. Acidic side always gives its hydrogen, while its basic side always has an OH. That's very important to know, since after all, water tends usually is neutral, so it works as an acid and a base. Yeah. When it comes to every other molecule that has to just divide them, and if there is no hydrogen, then I believe there is no correct way to put it. It can go either way. If there is no hydrogen, well, you likely not see that. Substitution reactions is one. So substitution reaction is 1 to 3 steps: initiation, propagation, termination, and it takes place with alkanes. Single bonds only. So first we have a Cr and a Cr molecule, which is going to be by using UV light as the catalyst, which will create two chlorines with a free radical ion. This free radical ion is going to go over here and take this hydrogen, creating a ClH, and leaving this carbon with a free radical ion as well. Seeing this, the chlorine with the other chlorine with the free radical ion is going to then join up with the carbon and create a one chloroethane. I think, would that be a one chloroethane, or would it just be a chloroethane? And it's fine. So yeah, it's one chloroethane. So yeah, when it comes to this, just remember, same thing as before. H's, you don't have to order Markov's law. Just know free radical ions takes a hydrogen, and then the other one joins a carbon. It's not that bad. The only thing I would ask that you remember is the steps in, initiation, propagation, termination. Those are separate steps that you have to remember. Alrighty. We'll be done soon enough. Don't you worry. Just 3 more things left on the agenda. Alright, so an addition between monomers. Hold on. Alright, so an addition between monomers is, of course, an addition between two different monomers, more specifically two different alkenes. So you can see we have here an ethene and a propene. So you will add those to add those together, you will break the door bond, and they will get stuck together, and this is how you write it. Here we have the ethene, which is now an ethane, and here we have the propene. As you can see, this CH just goes down here, and it's simplified because, well, there's a door bond, it can't connect. And now you may be wondering, what's this parenthesis in this N doing there? It is an N, not an H. I will let you know. I have the handwriting of a doctor. Alright, so basically what this means is that this is just a segment of a larger polymer. And this is supposed to represent that if you continue doing this over and over, they're going to get stuck together because, as you can see, this C and this C are capable of connecting to more carbons. So they will, of course, try to connect to more carbons, which is why they're showing like that, because they can continue growing and growing. All right. All right. So let's now go over oxidation. When it comes to oxidation, it can only happen with alcohols. So let's say we will happen with a primary. So a primary alcohol, here as in an ethanol, will first be oxidized into an ethanol. Yeah, uh, yeah, it's an ethanol, and then it will be oxidized further into um a ethanoic acid. So yeah, alcohol, um aldehyde, carboxylic acid. That's the order of things. Now, of course, how you will get those through oxidation is that distillation, reflux. And of course, the process can be undone if you reduce. What's the opposite of oxidize? Reduce it? If you undo the oxidation, it can go back and forth. When it comes to secondary, it will create a ketone. Yep, a ketone, as you can see here. When it comes to that, I believe it only requires distillation to do that. If it does. If it is distillation, that is. So yeah, there is nothing after a ketone, so cannot react further, but I can go backwards. Now tertiaries cannot react further, so instead here's a picture of a cat. I should learn how to draw cats, my god. Alright, so an addition between a carboxyl and a hydroxyl. Yeah, I'm using those names now. Hope you enjoyed. So as you can see here, here we have a hydroxyl with two alcohols at its end, and a carboxyl with two. I think I did that wrong. Oh darn. Alright, addition to a carboxyl and a hydroxyl. Correctly this time. So as you can see here, we have a hydroxyl in one end and a carboxyl in another end. It will form this. As you can see, it creates an ester, an infinite repeating pattern of esters, that is. This n represents the amount of times you can do it, blah 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 blah. And as you can see, this process creates two waters. Why? Well, in the process of it, my apologies, give me a second. These two alcohols, these two OHs will form together. And by that I mean this one loses an H, this one loses an OH, and this C connects to that C. And of course, since I reject an OH, that creates water essentially. And yeah, that's it when it comes to the addition of carboxyls and hydroxyls. Now, I just did very small examples, but there are bigger examples of that. And they can be a little hard, and they can use different ones that connect in weird ways. This is just a simplified version, alright? Alright, well, thanks for watching. I hope you enjoyed it. A big special thanks to these people, to my three high school chem teachers, the teacher assistant, and all of my fellow IB chemistry students, which includes both Ariana and Isabella. I'm single them out specifically because they did help out with the video. I sent them a copy of an order copy of this video for them to watch and review, and also when it comes to Isabella, I did ask her to review my script, and by script I mean my bullet point of notes on what to say exactly. So yeah, that's why I was a little disorganized. I'm sorry if I stutter a lot. I'm very bad speaking. That's why I made this video, and but yeah, A big special thanks to all of these people, of course, and of course these two for helping make the video. And while we're talking about these two, Isabella loves organic chemistry a lot. She won't stop talking about it. And she definitely wanted me to tell you that she loves organic chemistry. Alright, well, yeah. By the way, if I, yeah, I've said everything I've had to say. Please enjoy the rest of your day. Have a good day.